All right, Zach, I think we're recording. All right, so two reactions that we're going to explore today. We're going to, hopefully from a frontier molecular orbital theory, explain what's going on. One of them we start with is if I take a cyclobutene ring. Cyclobutene rings are under a lot of strain. Okay, so a lot of strain energy here. If you think about it, we're taking an sp2 carbon and we're making it or asking it basically to be 90 degrees. Okay, so 90-degree angle here puts that under an incredible amount of strain. So when I have a cyclobutene ring, they prefer to open up. All right, just under thermal conditions, they prefer to open up. And typically, these will open up around 100 degrees. Classically and historically, these were done on a steam bath. So around 100 degrees, these are going to open. And the way that they open is very interesting. If you think about these lobes here, you've got an sp3 lobe here, you've got an sp3 lobe here, you've got a pi bond here, and a pi bond here. Okay? So what typically happens is this comes down to here. Let me do that in a different color since I have black as the dimensionality. So these electrons come down here, and these electrons, remember two electrons that are sitting in between there, right? We have electron here, electron here. Okay, so these two electrons come down. These two electrons then go here. And so what we actually do on these reactions is we open up. Okay. So this reaction is a 4N reaction. In that, 4 electrons are moving, okay, on our frontiers. So we have 1, 2, okay, so we have 1, 2, 3, 4 electrons. Okay, so it's a 4N reaction. So as Woodward and Hoffman were studying this, they made a series of really interesting molecules. And one of the molecules that they made was this one here. Okay, this molecule here. But something happened with this molecule that really piqued their curiosity and the curiosity of a lot of people trying to figure this stuff out back in the 50s and 60s, more than the 60s and the 50s. They heated this thing all the way up to 260 degrees and no reaction. And that was very puzzling in the day. Why won't this thing open up? Why won't it open up? And so as they went back and had some of their students, their grad students, make a series of molecules. They made a series of molecules that look like this. One of them was this, and I'll try to draw this in three-dimensional space. So coming out at me. They made a series of cyclobutenes that had different elements of symmetry. Okay? And so when they hit this one, again around 100 degrees, sure enough, this one opened right up. But what was puzzling in the day was the stereochemistry, in this case the regiochemistry. Only. Okay, they only got one product out, none of this. None. Okay? Why? Well, I thought, well, let's make the other isomer of this. Let's make the isomer, this is what we call the trans dimethyl. This is trans dimethyl 2,3-dimethylbutene, cyclobutene, okay? And they made the cis. So Zach, I'm gonna bring you over here. And they made the cis. So I don't know what that is. Bring you over just a tiny bit more there, Zach. Okay. So when they made the cis, oops. Once again, heating it to 100 degrees, they saw only one product. Okay, this one here, only. Only product, yeah.
Is it cis and trans because they're on, like, the methyls are on the same
You got it,
plane?
plain.
Okay.
Yep, and this would be cis, yes, correct. So technically, this is gonna be cis, 1, 2, so cis 3,4 dimethyl cyclobutene. So that's what that molecule would be. Okay, so they made these cis and trans, and they noticed that they're only seeing one product out. So what was going on? Well, we're gonna have to resolve what's going on with this system. They also made a series of molecules, starting with not 4N, but 4N plus 2. So 4N plus 2 turns out to do something a little bit different. Let's keep the mystery alive with that molecule there. When they made these molecules, this molecule, and heated it, no reaction. Okay? This molecule didn't prefer to come apart. So they made a series of molecules that look like this, and under thermal processes, they chose to cyclize. Okay. So when studied further, as Woodward and Hoffman did, they synthesized a series of chiral or regio-specific isomers of this, and they got some interesting data out. They specifically made this one, and upon heating, thermal, again to around 100 degrees, they only saw one product. They saw this product here. Likewise, when they made the other isomer of this thing, lo and behold, they saw the exact same trend in only one product. This one here. So they saw this specificity of these reactions. And so, as Woodward and Hoffman being both being very intelligent scientists, chemists, they explained this using frontier molecular orbital theory. This is where FMO comes from, this work. So what we need to do is we need to draw a diagram of this. So, I'll let you catch up a little bit. Emily's there.
I've built some endurance.
What's that?
I've built endurance
Built
over
endurance.
years.
I'll try to go a little bit slower on this stuff because I do want you to kind of absorb it as we're processing it together.
Like, it makes sense as we're going, it's just time consuming to draw out.
Yes, yes, very much so.
Yeah.
So, Woodward and Hoffman set out to explain this, and let's draw. Let's draw our possibilities of this thing. Let's see if we can do that. I'm gonna do it like this. Let's see how like this. Better board management here. I'm gonna run out of room on this board. 1, 2, 3, 4, 5, and 6. So their whole study really started with this system here. Can we explain what's going on, and can we explain what's going on over here? So when they did this, they began to look at the orbital set, and this is where the fun comes in. And back in the day, to actually be the minds that sit around and think this through and come up with what's going on and why is actually, to me, always fascinating. The minds that have done the science that we stand on, the giants that we stand on today in organic chemistry. And Woodward and Hoffman are definitely two of those giants, Nobel Prize winners. Ooh, not very good board management, that very top one, but you get the point. Okay. So with this, just like we saw with the Diels Alder on Friday, we have Psi 1, Psi 2, Psi 3, Psi 4, Psi 5, and Psi 6. These are solutions to the Hamiltonian operator. And just like we saw, we also have symmetry elements. So we're going to have the lowest with no nodes. Next one up with one node. So this has a node right here,
Okay.
right through there. Okay. And then 2 nodes. So 1, 2, whoops, 2 nodes, not 3 nodes. Conserve, yep. Okay, let's get rid of that, sorry about that. Go here, here, here. A couple different ways you do too, but that's one of the ways we can make that work. Oh, I'm still not right. I'm gonna get rid of my coloring. Actually, that was okay. I'll wait till I finish this, guys. So we're gonna go 1, we're gonna go here, and here, we're gonna go down, here, and here, and we're gonna go up. There we go. That looks better. We want the most overlap possible. That's why the first one I drew did not have the maximized overlap. So we have a node here and here. So those are our 2 nodes. Okay. Now 3, we could do 1, 2, 3, or we could do 1, 2, 3, And it doesn't really matter, they're gonna be similar energies, so let's do this one. One node, two. So 1, 2, 3, we'll do that. So 1, 2, 3. So there's an overlap there and a node here. Okay. Okay. 4 is going to be similar, except we're going to leave 2 bonded. So 1, 2, 3, 4. So we're going to do here, down. There's one node. There's another node. That one. There's no nodes. There's a node, and there's a node. So this one has 1, 2, 3, 4. Okay, those are your nodes. So again, no nodes, 1 node, 2 node, 3 node, 4 node, and finally the highest occupied orbital is going to be the one with nodes all over the place. Lots and lots of nodes. 1, 2, 3, 4, 5. Okay, so these are really your 6 possibilities of where your nodes go. Okay. Now, what's really important is to look at the symmetry of this. So with this, we're gonna have a plane of symmetry running through here. Okay, so with that plane, oops, that one's up there. So with that plane of symmetry, when I look at this, I say that is a element of symmetrical nodes, or symmetrical molecular orbitals. That plane of symmetry is the same on the left as it is on the right. When I look at Site 2 with this plane of symmetry is asymmetrical. Okay, so it's asymmetrical relative, again, to that plane of symmetry. When I look at that plane of symmetry for Site 3, let's say Site 2, look at it right through there. When I look at Site 3, what am I? Am I symmetrical or asymmetrical?
Symmetrical.
Back to symmetrical, right?
It's plane symmetry.
What's that?
Plane symmetry.
Yeah, this is a plane of symmetry, correct. Okay, and when I look at Site 4, I am
Asymmetrical.
asymmetrical, good. Okay, and you see what's going on here. As I go up to this operation, here I'm going to be symmetrical, and once again up here I'm going to be asymmetrical. Okay. So there we do. We've given all of our possibilities with a 4n plus 2 system. All right, this is the 4n. This is a 4n plus 2 system here. This is our 4n system that we're going to try to resolve. Can we really determine what's going on here? So with that, we have a 4n plus 2, which has 6 electrons. So we populate those in the lowest molecular orbitals, just like we've done up to this point. We can only put 2 electrons per molecular orbital, so we just have to populate the 3 lowest energy molecular orbitals. All right? Tracking so far?
Yeah.
Okay? So all we're doing is we're looking at 1, 2, 3, 4, 5, 6 carbons. Each carbon has 1 electron, 1 sp2 electron that it brings to the party. So if you think about it, Zach, I'll draw it right here and then I'll erase it. If you think about it, what we're doing is we're talking about this here. We're talking about the fact that this is a double bond, this is a double bond, this is a double bond. They each bring in 1 electron, 1 electron, 1 electron, 1 electron, 1 electron, 1 electron, okay? So I have 6 electron possibility of this conjugated system up here. Each one bringing in 1 electron. So we have 1, 2, 3, 4, 5, 6. So that's where we've populated. All right, that makes this our highest occupied molecular orbital. So I'll move this over for you a little bit. That makes this the highest occupied molecular orbital. And this the lowest unoccupied molecular orbital, the HOMO and the LUMO. Okay? Very similar to what we saw talking about the Diels-Alder. Now, we now need to draw the product and see what's going on here. So, think about the product, and Zach, I pointed to, I think you saw that pointed to this one here, yeah. So what's going on here? Well, this has two sigma orbitals and 4 pi orbitals, right? So I'm gonna have a sigma consisting of 2 electrons, 1, 2. I'm gonna have 4 pi's, all bringing 1 in. So I still have 1, 2, 3, 4, 5, 6 electrons in the product, but notice, 2 of them are in a sigma, 4 of them now are in pi. Sigma is a lower energy than a pi bond, so that's why our new orbital set is going to look like this. It's going to look like that, and it's going to look like pi. Again, this is increasing in energy. Okay, so notice this is going to be a sigma. This is going to be like we saw back in the day, sigma star, okay, very high energy. This will be psi 1, psi 2, psi 3, and psi 4. Okay. So all I did is I looked at, again, starting compound with 6 pi electrons and finishing product with 6 electrons, but they're in different orbital sets. Okay, so my sigma here is symmetrical, or they're favorable, lower in energy when they're overlapping. My psi 1, again, is going to be the lowest possibility, which is all in phase. And here is going to be one node, just like we saw with our diene on Friday. Okay. And then here we're going to have 2 nodes. Here and here. And finally our highest is going to have 3 nodes. Here, here, and here. And this is going to be out of phase. Okay, my highest. All right, let that sink in. That's really important that we see where these electrons are moving. Yes?
Can you explain again why is psi 3 over and why is psi 4?
Yeah, so psi 3 is the highest occupied molecular orbital. So the highest orbital in energy that has electrons. The highest orbital without electrons is the lowest unoccupied molecular orbital. So LUMO, this isn't the lowest, that's lower. So lowest unoccupied, highest occupied. Those are just what those are what those are called. Now with the Diels-Alder, what we saw is the electrons switched here. Okay, it's gonna be similar, but not exactly the same. HOMO and LUMO. Now, let's go back over here and see if we can figure out where these electrons go. Okay, each of those, again, I have 6 electrons, so I have 6 possible molecular orbitals, a bonding and an anti-bonding. That's where the 6 comes from. How many electrons do I have? Well, I have 6. Now, what is my symmetry element of psi? Or sigma, excuse me. What is my symmetry element?
Symmetrical.
Symmetrical.
Okay.
What is my symmetry element of phi 1?
Symmetrical.
It's also symmetrical. What is my symmetry element of phi 2, psi 2?
Asymmetrical.
Asymmetrical. And what is my symmetry element of psi 3? Symmetrical. Mm-hmm. Psi 4? Asymmetrical. Uh-huh. And sigma star? Asymmetrical. Good.
Mm.
Okay. Now, how many electrons do I have in my product? How many electrons?
6.
Still have 6. 1, 2, 3, 4, 5, 6. So they have to go somewhere. So I'm going to put them in my lowest occupied molecular orbitals. There they go. Now, here is the aha and the genius of Woodward and Hoffman. Notice this. And I'm going to try to talk you through this. Go ahead and draw all that, and then watch me up on the board here for a second. Have a little bit of my tea, because this is honestly the genius and the aha. If you follow this, which you will, you're going to have this. Okay. And here's really what's going on. This is symmetrical. Oh, go ahead. This is symmetrical to a plane of symmetry, right? Meaning I'm symmetrical through a plane. Okay? So relative to that plane of symmetry here, these frontier orbitals have to maintain symmetry. So I have 2 possible rotations, right? I have, Zach, I'll do it like this. I have 2 possible elements of rotation. Watch this. One is symmetrical to that plane. One is not symmetrical to that plane, right? So that's why when I'm symmetrical to this plane right here, I have what we call a disrotary or a conrotary, okay? Con with. It's going to rotate the same direction, either that way or that way. Disrotatory is going to be this way or this way, okay? But here's the key that Woodward and Hoffman figured out. Because you have a plane of symmetry, your symmetry element has to be consistent with your rotation. In a plane of symmetry, I can't have a conrotatory because that's not symmetrical to a plane. What's symmetrical is this, okay? So that's why these electrons go here. Oh, that makes sense. Notice they're in phase. As these come down and these come down, notice what does it make? It makes the new bond, which is symmetrical. Isn't that cool? That's the aha of the Woodward-Hoffman. Because I am what we call disrotatory, or we just abbreviate it dis. I'm disrotatory because I'm symmetrical to the plane. I now allow those electrons to migrate to the sigma bond. And watch what happens to our other 2 up here. We also have an asymmetrical that can go to an asymmetrical, and a symmetrical that can go to a symmetrical. Isn't that cool? And what forms with this is, notice, this is in phase, this is in phase, and this is in phase, and this is in phase. They're all in phase so they can form a new double bond. Okay? The sigma is in phase, and the 2 pi's are in phase. Isn't that cool? Good? Now, watch what happens when we do for n. And again, it's worth drawing these out because the more you see this drawn out, the more we're going to be able to answer our question, what's going on with this molecule? That's the whole, again, whenever, that's why I love, when you look historically in the sciences, you look at the anomalies. Oh, by the way, I should have, before I erased it, let's look at this one. That's why, notice this is where we're going to be, here's, my thumbs are the methyl groups, okay? Thumbs are the methyl groups, Zach, right here. And notice I'm going to go, okay? Or, what's my other way I could do this? I could go that, or I could do that, with that, okay? So that's why thumbs are methyls. As I go with, where do the methyls go? they go with, or with, they go trans. That's why this goes to this only. Isn't that cool? So let's draw, and this one here came from what? Well, when we had our methyl groups here, right? And we still are gonna do a disrotatory. Notice that? Disrotatory. Go back and look at your notes if you need to, but disrotatory, when I made that, or I guess it was this in your notes, they went dis, right? Or dis, doesn't matter, but same thing. They went to cis methyls. Okay? So, watch what happens when we go to, let's see, Zach, you got us. Okay, watch what happens when we draw the orbital set for 4. 4 is not as big. So, we're going to have, we're going to have 1, 2. Okay, we're going to have a sigma. And if you want to draw the rest of the molecule in, you're fine. And we're going to have a sigma. Okay. Likewise, when we look at our symmetry elements, that's all in phase with this. Okay. This one's in phase. This one's in phase. Or excuse me, and this one's out of phase. So, again, my symmetry elements, if I'm talking about a plane of symmetry, are, blue here, symmetrical, symmetrical, asymmetrical, asymmetrical. Okay? So when it opens up to this, 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 and this. Okay, and again, if I draw all these, so again, no nodes, 1 node, 2 nodes, 3 nodes. And relative to my symmetry function, I have symmetrical, asymmetrical, symmetrical, asymmetrical. But here's the problem. We've got a big problem. We have a big problem with our symmetry, because watch what happens. If I'm starting, am I using black for these? If I'm starting here, again, remember the system. This is the system. Actually, backwards, sorry. So the system is going from this to this. That was the original reaction in your notes. And I said that it's a thermal process that likes to open up. Watch what happens. I'm no longer symmetrical. Because what happens are these electrons, I'll use red here. These electrons can go here to populate. But notice what my symmetrical element has to do. So something's wrong. This doesn't work. So how do we resolve this problem? Well, we resolve it. I wish I would have brought green. Let me see if green's in here. We resolve it by understanding that we have a different symmetry element.
I have a
Do you have one?
green.
Oh, you have a green? Awesome, you're awesome. Thank you. Okay, so watch what happens. This symmetry element here assumes what?
It's a triangle.
No, what's it assume? What have I been doing the whole time?
Are you talking about the asymmetry?
Yes. Okay, it's a plane of symmetry, right? But so the blue is a plane of symmetry. But there's another symmetry element.
Rotation.
It's rotational symmetry element. So what happens if I have a rotational plane element? So instead of a plane, I rotate this all the way 180 degrees. Notice, I am still, and I'm going to do green with rotation. Blue is plane. Green is rotational plane, okay? So am I symmetrical or asymmetrical here? If I move this all the way around, what happens?
Symmetry.
Symmetrical. Okay? If I move this one all the way around, what happens? Asymmetrical. If I move this one symmetrical and asymmetrical, right? Because this is going to go out here to white, so it's not, so it doesn't give me the same thing when I rotate it. Okay? What about here? Again, this is rotational. So what about here? If I rotate it all the way up, what am I?
Asymmetrical.
Asymmetrical. What about here?
Symmetrical.
Symmetrical. And here,
Asymmetrical.
asymmetrical.
Symmetrical.
And here, symmetrical. So what just happened when I changed my rotation symmetry? We'll look at my orbitals. Now my orbitals are aligned. Those can go there, and those can go there, and I never have to cross the energy threshold of antibonding. But what was my overall symmetry element? It was rotational, not plane. So this is why if it's plane, we have disrotatory. If it's rotational, we have conrotatory. So here is the very first Woodward-Hoffmann rule that you want to ingrain, because again, we're going to build on this a lot. We'll build on this whole week. The very first, thank you for that, by the way. The very first Woodward-Hoffmann rule starts with this. 4n thermal con. Okay? You have to absolutely memorize that. That has to be one of those, just like what do I mean when I say a strong acid? 100% dissociated. Remember those types of things? 4n thermal con. 4n thermal con, 4n thermal con, 4n oxyloss, oxyloss. A lot of those little oxidations, loss of electrons, oxyloss, oxyloss, like, okay? All those types of things over the years that we have been talking as a class, this is absolutely crucial to understand the next 3 chapters. 4n thermal con is where all the rules start. So notice this dilemma here. 4n thermal con, 4n thermal con, 4n thermal con rotation, 4n thermal con rotation. Okay? Con. Which is why, notice what happens here if I am con rotation. Let me erase this guy. And watch what happens when I do a 4n thermal con and see if we can resolve what's going on here. 4n thermal con. 4n thermal con. Okay? Let's do pinky thumb chemistry. And watch what happens. Okay? Here's my bond. My pinky is my bond, right? Pinky is my sigma. That's going to become pi. But which way do I need to rotate? 4n thermal con. So here we go. What just happened? Where'd my hydrogens go? Weird.
It's going with the
Yeah, so they're going, so watch what that actually does. 4n thermal con gives me this weird, no, not that. Gives me this. If it went dis, which it does not, notice, I should have done that in green. Let me bring it green over. Well, that's okay. That, just make that in green, because that's, well, let's do green. Let's keep
Go
it,
for it,
yeah.
yeah.
Yeah, keep that consistent, because that does help. This should have been in green, because remember, this is the con rotation, 4n thermal con. Puts a trans alkene in the middle of a benzene ring. Not gonna happen, okay? If I went thermal, dis, notice, 4n thermal dis would give me benzene. But notice, 4n thermal dis gives me benzene, but because I am not symmetrical, we see none of this. Because this molecule, you would say, man, I know aromaticity is bomber good. I know this strain cyclobutane ring wants to open up, but it can't open up because of the asymmetry of the plane. It has to go 4n plus 2 con rotation to go to this, which is why we can beat the tar out of this molecule, and it basically just decomposes. We don't see benzene, and we don't see this. Isn't that classic? I mean, that is classic, and it's all explained through symmetry elements. Isn't that cool? Questions on that? I don't know if you saw that right there. That's benzene. Okay? So here's what you want to do. And by the way, you could do the exact same thing over here. We could have done this green as well. I won't. But we could have added green to here and done green as a point instead of a plane. So again, you're going to have asymmetrical, symmetrical. It's going to be asymmetrical, symmetrical, asymmetrical, symmetrical. Okay, and you'll see that you have to go up to a higher one. You can't just have the bottom three, because remember our energy is across. Here's our cutoff. Our cutoff kind of goes through here. Okay. So if I keep all of my bonding orbitals going back to bonding orbitals without having to cross up into a higher energy, it's allowed, we call that. So 4n, and that's where 4n thermal con is allowed. Which means 4n plus 2 is thermal dis allowed. And that is the first two rules of Woodward-Hoffman. I like to think of it as start with 4n thermal con, 4n thermal con, 4n thermal con. Because what you're going to see as a trend through here is if it's 4n thermal con allowed, it's going to be 4n plus 2 thermal con disallowed. See, it all builds on one. And here's where it's going to get real fun on Wednesday. We're going to jump into photochemistry. Because photochemistry throws all of this upside down. So it's going to be 4n photo dis, yeah, and we'll see why. Cool.
I have a question. So whenever we do this, is it only for, are we just looking the dienes in symmetry?
Mm-hmm.
And then if it's on only rotation?
Yes, you can think of it that way. Yeah. Yep. So con is, yeah, con is plane, or excuse me, dis is plane, con is a point, yeah, point rotation. Cool? Kind of fun, right? Again, I'm always amazed at the minds that come up with stuff like this to try to, you try to make a molecule to really confirm this thing. Because this thing should just open up beautifully to benzene, right? Everything's there, except of symmetry. Crazy cool.
Yeah.
Yeah, really nice. Yeah, John.
For that one,